All right, good afternoon, folks. Back in the early 1970s, an absolutely amazing group of people came together and became what we know of as Xerox PARC and created most of what we now know to be the underpinnings of the personal computer revolution. In those days, they built devices that had bitmap displays. They created the Ethernet. They commercialized mice. They created scalable fonts. And they created networks of systems, networks of personal computers, not just isolated devices, and explored many of the software technologies that we know today. Our guest today was sort of at the heart of all of that. He was the architect of the Alto personal computer, which as a young graduate student I can say was a deep inspiration for me in my computer architecture work, and maybe we'll learn a little bit more about that today. He was also co-inventor of the Ethernet, deeply involved in creation of the first commercial laser printer. He has been recognized broadly for his achievements. He won the Charles Stark Draper Prize in 2004, the John von Neumann Medal in 2009, and the ACM Turing Award. I'm sorry, the von Neumann Award in 2007, and the Turing Award in 2009. Truly amazing accomplishments. Please join me in welcoming Chuck Thacker.
Well, thank you very much for inviting me. When Bob asked me to give this talk, I said, well, what would you like me to talk about? And he said, oh, talk about the Alto architecture. And I said, Bob, the Alto architecture was 40 years ago. There's nothing interesting in it today. But looking back over it, I decided there are some perhaps interesting things and lessons for people in the 21st century that we hadn't yet learned in the 20th. So here is a roadmap for the talk. First, I'll give you a little bit of the history because this happened before most of you were born. I'll talk about systems research at PARC, the labs, the timeline of those labs, and where we got our ideas. Then I'll talk about the Alto itself, and then the architectural details, which are the technical part of the talk, and describe some of the Alto-related hardware that we built at PARC, and describe the software that ran on it, because after all, without software, a computer is no better than a hot rock, as we have learned over the years. I'll talk a little bit about the attempts we made to actually make money on it, none of which really succeeded. It took others to actually turn many of those ideas into money, and some people have done spectacularly well at doing that. I was interviewed by a Microsoft reporter when I got the Turing Award a couple years ago, and he asked me what I thought the effect of my work on Microsoft was, and I said, well, there's a fairly good chance that if that work hadn't been done, Microsoft would not be here today. That never made it to print. But so what went on at this crazy place? I mean, you've all probably driven by it and seen it. It's up on Coyote Hill, although that wasn't where it started. It actually started down on Porter Drive in a building which has now been demolished. But it was a very interesting experiment. It was set up by Jack Goldman, who was the director of research for Xerox at that time. And Xerox already had a perfectly good research laboratory in Rochester, New York. But they primarily did work on copiers and things like that, and they didn't really understand electronics or computing or anything like that. But they realized that it was somehow likely to be important. So they said, well, let's set up a lab. And they hired George Paik, who was at that time the provost of Washington University in St. Louis, to sort of figure out the whole thing. Now, George was a physicist, and so he thought organizing a lab like an academic department or a group of departments would be a good thing. But initially, the biggest question was where to put it. And of course, people wanted it to be in New Haven so they could be next to Yale, not realizing that Yale didn't have a very interesting computer science department. And then they thought about Utah and a few other places. And finally, they settled on Palo Alto because Palo Alto had Stanford right next door and Berkeley up the bay. And so they decided that in about 1969. And by 1970, they had hired Bob Taylor to start the lab. And I'll talk about that a little more when I get to the timeline part of the talk. So the main tenet at PARC was that if you really want to understand the value of a system, a computer-based system, then you really have to build it and use it yourself. And if the users are the builders, that is a tremendously powerful bootstrapping effect, as had been noticed earlier by Doug Engelbart. This actually caused us to miss a few things. We got word processing, we got printing, we got networking, we got distributed computing. We didn't get spreadsheets. Why? Because we didn't need spreadsheets. Now, it turned out that Peter Deutsch had written an interesting memo describing a system that he called spiders under the paper. And the idea was you would write something on the paper, and the spiders would go around and interpret it in various ways. But it never got built because, again, we didn't need it. We needed text editors. I mean, those of you who write papers today are probably not amazed by how easy it is to get camera-ready copy. Back in those days, I see one person who's done it. You used to get from the publication a board with outlines where they wanted the paper to go. You would type it, or your secretary would type it, and then you'd cut it up to fit the outline and rubber stamp it to the board. And when all that was done, you would send it into the publication, and they would make photo offset press masters for it. And in fact, it's interesting because the first submitted PhD thesis that was printed on a laser printer was Lois Lampson's, Butler Lampson's wife. She submitted it to Berkeley. And the person in the department looked at it and said, "Which is the original?" And she said, "Well, kind of either one. They're both the same." And he said, "Come on, one is a photocopy. Which one is the original?" And it took quite a while to get them to understand that that the world had just changed out from under them. So the highest priority at PARC was actually hiring the best people. You don't want to hire turkeys because they tend to demotivate the group as a whole. So the main sources initially were, I say, the BCC mob. And Berkeley Computer was a company that had been started in 1967 out of a group of people who worked at the University of California, Berkeley, on the SDS 940 time-sharing machine. And we decided to build a follow-on, but we looked around and discovered that within the constraints imposed by the university's overheads, it was not possible to do it in the department because although the 940 could have been done, the BCC 500 machine was a much larger scale enterprise. So we had to go to New York to get venture capital, which we did, and started a company in the industrial district of Berkeley. If anybody of you ever driven around Berkeley, it was on 6th Street, which is even today a pretty dreadful place. But in 1970, the recession wiped out Berkeley Computer, although we did complete the time-sharing system and sent it off to University of Hawaii, where it served for several years as the departmental computer. It fit in one 747 along with 20,000 pounds of dried milk. We got people from Utah, Stanford, SRI, CMU, and MIT. And the important thing to remember when starting a laboratory, which is a very fragile thing, is that good leadership helped. And we had Bob Taylor, and that was something nobody else had. And so we had the edge on everybody. So the organization for PARC as a whole was a computer science lab under Taylor and a guy named Jerry Elkind. System sciences lab led by Bill Gunning, later Harold Hall, later Bert Sutherland, a brother of Ivan Sutherland. The General Sciences Lab did physics. That was Jerry Lukowski. The Optical Sciences Lab was led by a guy named John Urbach. And later we had an integrated circuits lab, but this turned out to be a singularly bad idea. We spent about $15 million on a fabrication facility for ICs, and it never really worked very well. And the lesson that we learned was you can't run a fab line building nothing but prototypes. You've got to run product through it continuously in order to keep it working and optimized. So timeline, in 1970, PARC was founded. In 1970 through 72, we concentrated on growing the lab and building the critical infrastructure. We built a thing called the MAX time-sharing system. That was for multiple access Xerox computer. And it was also a pun on the name of Max Palevsky, who had recently bought or sold to Xerox Scientific Data Systems, which was at that time a competitor to DEC. And he sold it to them for $1.5 billion. And he's reported to have said later that I'm the only person who's ever sold a dead horse for that money, for that amount of money, while the horse is still standing. In 73, we built the Alto. It took relatively little time to actually do it because we had had the experience of Max to rely on. And SSL built a similar system called Palo's PARC Online Office System, which unfortunately suffered from the fact that its displays were character terminals, not bitmaps. There are two good ideas in the Alto. One is the bitmap display, and the other is the multitasking scheme, which I'll describe later, but everything else is duck simple. In 1974, SSL built the year's printer, Ethernet, Alto, Research Character Generator, and slot. And this was the very first laser printer. And the guy who did it was, well, there were several people, but the primary optical engineer was a guy named Gary Starkweather, who had worked at the Xerox lab on the East Coast. And he had this idea, and he couldn't get any traction for it, so they sent him to the West Coast. And he proceeded to take apart a standard Xerox copier and mount a very complicated scanning polygon to scan the lines. This printer ran at 60 copies a minute, and it had 600 dots per inch. So it's pretty good even by modern standards, although it was extremely expensive. Between 75 and 80, we had a lot of applications and other projects that we did. And yeah, in late 77 through 1983, we tried to make some money at it. Most of those trials were unsuccessful. And then in 1983, the computer science lab dissolved due to some arguments with the management. And many of us went off to DEC, to the Systems Research Center in Palo Alto, where we spent another 13 years. And then I went to Microsoft. Although a little later, a lot of the colleagues that I had from CERC and at PARC got together to set up the Microsoft Silicon Valley lab. So I'm working with people that I've worked with for 40 years. So this is what computing was like in 1972. This was the Max machine. It was the end of an era. The four cabinets on the right were, for a short period of time, the largest semiconductor memory in the world, 3.2 megabytes. The next two cabinets going to the left were the CPUs and the console machine. And that thing down in the lower left-hand corner is a multiplexer for 32 console teletypes, terminals. And we built a couple of these to be the department's, the computer science lab's primary time-sharing system and serve most of the computing needs of the 40 or so people in the lab. And this was actually a PDP-10 clone, but Xerox had paid all that money for SDS. They wanted us to use one of their machines, the so-called Sigma 7. We looked at it, and it was completely unsuitable for time sharing and would have required a lot of work. And we said, well, we'll just build a DEC 10. And so we did. And it was pretty successful, although there was one little problem. Okay, well, I'll tell you about the problem in a minute. So where did the ideas for personal computing come from? Well, they were all over the place. It was, in some ways, it was the right time, except for one thing. A lot of people had been talking about it. Vannevar Bush, who was Roosevelt's science advisor during the Second World War, wrote a paper an article for the Atlantic Monthly in 1945 called As We May Think. And he described in it a machine called the Mimex, which was supposed to help scientists. I mean, this was science fiction, right? But it had, you know, screens and a memory. He thought photography would be the basis for that. And it got a lot of people thinking about what computers, which were at that time brand new, might be used for and useful for. And a lot of people thought, well, of course, computers were used in the Second World War, mostly to figure out whether the atomic bomb was going to go off or not. But late in the 60s, Licklider and Taylor, who was now working at ARPA, the predecessor of the Defense Advanced Research Projects Agency, wrote a paper called The Computer as a Communications Device. And a lot of people read this paper and didn't understand it. I didn't understand it. And many of my colleagues didn't. And then finally, the thing that really got us thinking about this was a thing called the mother of all demos. And if you give a search engine that as a query, you can see an hour and a half of the most amazing things happen. It turns out that Doug Engelbart, who is the guy who invented the mouse, had a system called the online system, or NLS, and he did a demo at the Fall Joint Computer Conference in 1968, made a movie of it, but he sat there, he had one of the first large screen projection televisions, and it could either watch what he was doing or focus on the lab at SRI down on the peninsula. They got a lot of television lines from the phone company, and so they were able to run the system as it sat in SRI from the stage at the Cow Palace. And several books have been written about the Alto and the PARC environment and so on. And one of them is called Dealers of Lightning. And we didn't do that. What I've said all along is that we sat there, and I didn't see it in real time. I saw the movie a little bit later. We sat there and we watched Engelbart literally dealing lightning with both hands. He had the mouse in one hand, 5-finger keyboard in the other, and he would occasionally move to the real keyboard and type things. Really amazing demo. And then, of course, there's Alan Kay. Alan has been pushing an idea for all of 40 years, which he's still polishing up, which is an idea of a thing called the Dynabook, which is manifested in his language, which is Smalltalk, called various other things, and still available today. And then finally, there was the BCC mob. That was myself, Butler Lampson, Peter Deutsch, Dick Schaup, several other people from Berkeley Computer. So what was it? Well, there it is. If you've gone over to the Computer History Museum, you can see one, but it doesn't work. To the best of my knowledge, no Altos work. The Computer History Museum has been trying to convince me that it would be a good idea to reconstitute one, but I think it would actually be a challenge because of a lot of the technologies that went into it that either no longer exist or are sure to have died between then and now. But it had a display which deliberately was operated in portrait mode rather than landscape mode because we were, after all, interested in building office systems, and we wanted our displays to look like paper. And since you could do anything with that display that you could do with paper in terms of marking, as long as you were willing to write with just one color pen. That was clearly the right choice, so we did that. We designed our own keyboard, and that took about 3 months because we would fight about the layout of the keys. There are a lot of funny keys on there that aren't on today's typewriters, like left arrow. There's a mouse to the right. We took Engelbart's mouse and actually modified it to be digital. The original mouse was actually analog. It had a couple of potentiometers and analog to digital converters, but for us, analog to digital converters were too expensive. So we fixed that. And the cabinet over under the table to the left is the Alto itself with its cartridge disc. And it used a 12-inch cartridge disc, which had the amazingly large amount of storage, 2 megabytes, 2.5 megabytes. And so typically everybody had racks of these things, and you would keep one particular project on one disk and plug it in when it came time to work on that. So why might it be interesting today? Well, historically it's interesting because it was probably the first personal computer. There were some other machines before that, notably the Link, which was built by Wes Clark at Washington University, which were actually used for one brief summer by one person in their home. And so it might qualify. There were a lot of computers where you could sneak in at night and be the only user, so those might qualify. The TX2 at Lincoln Labs comes to mind. But certainly the Alto was the first machine that was designed from the get-go to be a personal machine, and which was replicated in large enough quantities that it actually got some traction. It had one problem: it was too expensive. And the reason for that was the technology of the time wasn't good enough. But we were a research laboratory, and so what we would do is we would spend money to simulate the future. Now, that's getting harder and harder to do these days because we are limited by what our semiconductor fabrication facilities can produce, and everybody plays with the same chips. So that's harder. The other reason is that it was a platform. I said earlier that without software, computers no better than a hot rock. And Alto had a lot of software. And there was a lot of software that was written for it, and a lot of hardware that was based on it that used it as in a central role. For instance, it was the A in the ears printer. It was the controller for most of the laser printers that followed. And the other thing is that university computer science departments used it. We had a university program in which we would give a Dover laser printer plus 6 Altos to a university that wrote a reasonably cogent proposal for what they were going to do with it. And I think we did that for about 10 universities, of which one was CMU. And there were Altos, for instance, in the Carter White House. And they were used for production of memos and so on. When the Republicans came into power, they didn't understand what they were, and they had them all thrown out. But a lot of people learned programming on the Alto. And it wasn't a commercial success because of the cost, although, of course, laser printing paid for PARC for basically all of its life, because Xerox made a bundle on laser printing. Not as much as they would have liked, because they missed the idea of low-end entrants coming in with something that is not as good as they can do, but much cheaper. And so they watched the Japanese just crawl up market at them. But they managed to not go out of business, which several other companies who've made that mistake have. So what were the technologies? Today, everything is silicon gate CMOS, complementary metal oxide silicon technology. That was not the case at all at this time. In 1973, no one knew how to make a p-channel transistor. And so everything was in channel, And even before that was metal gate PMOS, where the gate was metal, and there's a dielectric, and then there's a channel underneath it, and that's a P-channel device. But it was originally used by Intel to make the first successful dynamic random access memory chip, the 1103. And we got those things in order to build Macs, and we reused the board technology in the Alto. And there was only one problem with it, and it's that it didn't work. We thought it worked because I had been very careful when I designed the memory system to provide an extensive error correction facility so that if the memory made an error, it would correct itself. And it would only mark the error if you had two errors in a single word, which basically never happened. And we thought when we built the Alto that the max memory had worked so well, it was basically error-free for years, a couple of years, that we would just use those boards and we wouldn't even bother with error correction. We'd just use parity. And then we found something out. It worked fine for a while, and then as we started running real programs and did more complicated things with the machine, we began to see errors. And I thought, well, what's going on here? They work so well in Macs. And I went back and I reviewed the situation. And as I said, I had put a lot of error correction into the Macs memory just to avoid this. But I also put logging counters and so on so that the programmers could access those counters and print out reports and this, that, and the other thing. And what I discovered was that the software guys hadn't used them. They just ignored them. And so the machine had sat there for a couple of years making a gazillion errors and working flawlessly nonetheless. So that was a mistake, and it basically set up an arms race between me and Intel. But the race was won finally in 1975 when 4K by 1 RAM was introduced. And then in 1978, 16K devices were introduced. The boards were wire wrap, and I have a picture a little later of how that was done. And we also used a technology called stitch welding, which was an amazing technology developed originally for the space shuttle. And as I say, there wasn't any CMOS yet. So there's 96,000 bits in 1972. That's a board about this big. Today, you can't see 96,000 bits. It's too small. I'm working with a chip these days that has 450 so-called block RAMs, each of which is 32,000 bits. So that would be 96,000 would be about 1% of the total memory on that chip. On that chip, you could fit several hundred Altos with their memories and disks. So here's the lab in which it was done. And Alan, as usual, stealing the show by standing in front of the machine. That's a younger version of me, Ed McWright, who was my partner in crime, who did most of the disk stuff, and Larry Clark, who was one of the technicians that worked on Macs and then on the Alto. And of course, this is interesting because this has one of the boards that we used, but it also displays Alan in one of his moods. If you can see on the screen of the Alto, that is the Sesame Street Cookie Monster. And that is an animated graphic of the Cookie Monster eating a cookie. It is, as far as I know, the very first animated graphic that ever appeared on a computer screen in the world. I've had about 3 true aha moments in computer graphics over 40 years. This was the first one. The second one was when I sat down about 12 years later and flew the Microsoft Flight Simulator on a CGA PC in color, 8 colors. And I was a pilot at the time, and I realized when I got up from a half-hour session of that I had sweaty palms. So something was going on there. And the third was when I first saw the Doom video game running on a PC. The fact that you could make that realistic of graphics, and of course that was terrible graphics, but it was late 80s. And today, of course, we can make almost anything, including very high quality movies and so on and so forth. But this was kind of the beginning. And if you count carefully, you'll find 3, 4, 5 by 10. I think there are about 50 integrated circuits on this board. And it took about 5 of those to make an Alto. So here's some comparisons in the technologies that were used today in my home PC and the Alto in 1972. And the factors are interesting. It costs about, the Alto costs $15,000 or about $105K today. My home PC cost $850. Factor of 125, that seems pretty good. The clock rate was 6 megahertz. Today it's 2.8 gigahertz, factor of, and there are 4 cores, so it's a factor of 1900. The memory size is an interesting one. I have 6 gigabytes of memory in my home machine. We had 128 kilobytes in the Alto. That's a demonstration of the power of Moore's law, factor of 48,000. Memory access time was not all that different, factor of 17, but compared to all those other numbers, that's small. So memories haven't gotten much faster, and processor clocks have gotten a lot faster. And of course, this is the thing people call the memory wall. The display was reasonably high resolution, about 500,000 pixels. And now it's 150 times larger. But that's okay, and it doesn't need to get much better because we're now at the limit of the resolution of your eyeball. So displays really don't need to get a whole lot better, no matter what Apple tells us. The network is only 300 times faster, but amazingly enough, it is the same old Ethernet. I mean, it's not the same, of course, but a lot of the numbers are the same, and the name is the same. And this is a really great example that if you have a cute name, reuse it, right? Keep using it. Jack it up and drive a new technology under it, and it'll be accepted. The disk capacity is the best one, I think. The disk guys have the semiconductor people beat out solidly. 280,000 times the density. Yeah, they really go for it. The other thing, Rob Pike once pointed out to me, there's one other thing that we don't think of as an enormous advance in computing, but of course it is, and it's the ability to make clear glass in the form of optical fibers. It used to be that you couldn't make glass that was clear, and so light would travel a very short distance before being attenuated. And now it's the case that if you filled the Pacific Ocean with the kind of glass that's used to make fiber, you could look at the bottom. Okay, so here's the technical part. This is the Alto processor. And computers at that time, can you see this slide? Maybe I will wander a bit. Computers at the time usually worked by having a central processor and a memory, and they talked to one another over the bus. And there was, in the middle of that, there was an arbiter that said, if the I/O devices want to talk to the memory, then they get priority and the processor waits. And the observation that we made was that, well, we're not going to implement the processor directly in logic. We're going to use this technique that had been developed called microcoding, developed by Morris Wilks at Cambridge. And so while the processor's waiting, maybe it could do other things. What might those things be? Well, we could run another process, but we didn't understand multi-threading at that time very well. So we said, oh my goodness, we could do some of the I/O work. And so that's the way the Alto worked. Rather than having one thing that it did, and then when the I/O devices wanted to talk to the memory, it would stop. Instead, it would launch a memory request, and then it had a few cycles, in fact 5, to do other things before the memory would actually deliver the data. And so what happened was we kept 16 simultaneous tasks, which today we would call threads, of course, and we kept their program counters in this thing called the MPC RAM. And the microprogram was contained in the PROM and RAM arrays. Originally, we used PROM, that is programmable read-only memory that you wrote once and then erased by shining ultraviolet light at it. And we later switched to RAM. RAM was also used for a debugger that we had. We could actually real-time debug microprograms on the Alto. And the instruction formats were actually kind of weird. We missed something here because if we had been more adventurous, we could have probably invented the RISC about this time. But we weren't adventurous. So we used microprogramming. Microinstructions were delivered up from the memory every cycle and placed into the microinstruction register. And note that they also went back into the microprogram counter RAM on this next address bus. So the micro machine did not have a program counter. It had 16 of them, but they weren't counters. Each instruction contained the address of its successor. So in fact, rather than stepping through the program, you could leap around in various ways. And branching was done by ORing bits into the low order bits of the instruction. And that was very fast and worked very well. So 10 bits of the 32-bit microinstruction address were used for the next address field. The remaining 22 bits were divided up as shown there. There was 5 bits of register select, 1 bit of so-called bus source, 4 bits of ALU function, a thing called load L and a thing called load T. Those are the L register down there and the T register there, and 2 function fields. And the function fields were used for a lot of different things because they were actually task specific. So, but this encoding is not particularly regular. It's quite ad hoc based on the needs of the I/O controllers that we were designing. So over the years, we added to the Alto, we added those S registers, which made the available fast storage larger. But the basic idea was that you could plug into the Alto's backplane other controllers like the disk controller and the display controller. It's been 40 years and we still can't get mice right. I'm not controlling this mouse properly, or the computer isn't responding to my gestures properly. So the primary controllers in the Alto were the disk, the display, and the Ethernet. And the display task would basically, every horizontal field, every vertical field, it would wake up, initialize some counters, and then every scan line, raster scan line, it would wake up and it would load a buffer with the data for that, for the next scan line, and go to sleep. The display took 3/4 of the processor when it was running. So we carefully optimized it so that if you had white space, you didn't have to use the memory bandwidth. Of course, if you wanted to do something like draw a full-page image, you needed it, and in that case, we used about 3/4 of the bandwidth and 3/4 of the storage. So we were very, very careful with those kinds of applications. I wrote one, and it was not fun. Yes, the thing to note is that the primary registers have only one read port. If we had decided to put 2 read ports there, we could have done it in a different way, and we would have basically built the first RISC. But as I say, we were cautious. And the reason that we were cautious was because we wanted to emulate this machine. This is a Data General Nova. Now, Data General is in itself an interesting story because it's an offshoot of DEC Digital Equipment as well. The guy who started it wanted to build and run the PDP-11 line, a guy named Edison DeCastro. And Ken Olsen wasn't going to let him do that. He was happy to have him be a designer, but he didn't want him to be a line manager. And so DeCastro quit and started Data General, completely redesigned the machine and came up with this machine called the Nova, which is actually an interesting machine in itself from an architectural standpoint. The Nova has 4 accumulators, AC0 to AC3. It has a 17-bit adder, a 17-bit shifter, a thing that can test for whether an instruction should skip or not, and a little bit of logic to handle the carry that comes off the left end of the addition. And you could do a surprising number of things with this machine. You could do them quite a bit faster than a PDP-11 would do them. And we ran a mess of bake-offs. We knew at the time we didn't want to write assembly language. And the PDP-11 had been designed for the assembly language programmer. You could write the most amazing things in PDP-11 assembler, and it would work. However, compilers weren't that clever at that time. And so they tended to emit somewhat longer sequences, which actually ran slower than the simpler sequences on the Nova. Now, the Nova couldn't do too much, but it could do it real fast. And so I still have a soft spot in my heart for the Nova, but it was also a 16-bit machine, of course, as most mini computers were at the time. That's, of course, the largest single mistake that a computer designer ever makes. And everyone has made it. I've made it. I've actually made it a couple of times. We made it in the design of the Ethernet. It's not providing enough address bits. Okay, in the case of the Ethernet, the original Ethernet boards had 8-bit addresses. Well, that was a big network in those days, but it's not today. And of course, the internet guys blew it too. IPv4 addresses are 32 bits. And I never quite understood that, because it's quite clear that they had a perfectly good, unique 48-bit address in the form of the Ethernet MAC address. Why did they choose 32 bits? That seemed crazy at the time. But they're suffering for it today, and now, of course, we're out of IPv4 addresses, and we have to go to things that aren't as good, primarily from a security standpoint, like NAT. So in any case, this was the emulated machine. It was there were 4 basic instruction classes. This is not quite a Nova. We changed it a little bit because we didn't want Data General to sue us, and so we made indirection work slightly differently. You could have only one indirection. In the Nova, you had an indirect bit associated with every instruction, and you could dance your way through memory following a long indirect chain. Who cares? Nobody did. So he took that out and said there's only one level of indirection, and that means that an effective address gets one more bit. So instead of building 64 kiloword machines, we could build 128. So the memory reference instructions were basically load and store. And if you look at those first 3 bits, you find that the instruction set is Huffman coded. That means that there's one class of the 4 that uses bit 0. That's the accumulator to accumulator instructions, and then uses the other 3 bits for something else, the other 2 bits of that 3-bit field. That's why the load and store functions are 1 and 2. 3 is the special function instruction, and that was added for the Alto. And of course, 0 is jumps and jump to subroutine, which would save the return link in accumulator 3. Increment and skip if 0, and decrement and skip if 0. Those were the only conditional branch instructions in the Nova. And it was an incredibly good idea, because what you would write, or what the compiler would write for you, is code that, for instance, at the end of a loop, would skip over a jump instruction if the loop was done. Otherwise, it would jump back to the beginning of the loop. Very efficient loops in the Nova with very great simplicity. That idea was later adopted by ARM and given the more pretentious name predication, but it's the same stuff. They read the Data General manuals. Okay, where are we? Oh, here's the matrix of how we connected up I/O devices to the Alto. There were a lot of different kinds of I/O devices that were built. Some were built by us, some were built by others. The most fun one that I ever built for the Alto is not in this table. It was a digital organ for Alan Kay. Alan was an amateur organist. I will not say accomplished, but amateur. Alan now has in his music room in Hollywood, in his home in Hollywood, a full-size pipe organ, which he had built. And I asked him what his neighbors thought about this, and he said, well, I had to build some really thick walls. But his first organ was electric, and what it was now what we would call wavetable synthesis, which is an obsolete technique. You just play through the wave shape, and the microcode did that in response to touching a key. We bought a 3-manual organ keyboard with pedals, so you needed 10 scanning threads looking at the keys, 1 for each finger, and 10 fingers and 2 toes, 12. And that was fun. So we plugged things into either the processor bus directly, and those were the guys in the lower right-hand corner primarily, the display, disk, and Ethernet controllers. The raster printers and the laser printers mostly plugged in that way. And the Ethernet and ultimately the ARPANET interface plugged in that way. The mouse was actually handled by an offshoot of the the horizontal task, which ran at 44 kilohertz. So every 44 kilohertz, you'd take a look at the mouse and decide whether it had moved and increment or decrement a location in memory. And that's the way we did mouse coordinates. Today, it's much, much more complicated, which is why this mouse doesn't work. I wish I knew whether that was Adobe or Microsoft. Low-speed devices, there were a few, not too many, because there weren't very many interesting devices in the 70s. Nowadays, everything that is USB would be handled that way. How are we doing? 4 minutes. Okay. Any questions about the technical details? We're pretty much done with those. I can answer some specific questions. Yeah.
Besides Smalltalk, what programs were tended to be used?
Next slide.
Sorry?
Next slide. So the other hardware that we built, well, we built ears. We built the Dover printer, another printer called Orbit, which wasn't as successful. We built a color printer. Xerox knew how to do color xerography, and we built a thing called the Puffin. And of course, the one that actually made the money was the Xerox 9700. Other computers, we built quite a few. After building the Alto, I went off and designed a machine called the Dolphin, which was designed to use more modern technology and included the first color display that we had. But it wasn't enough, and also had virtual memory. That was a new thing at that time. But it was not enough faster than the Dolphin, than the Alto, that it became popular. And so the machine that was popular was the Dorado. The Dorado was an amazing computer. It took 3 years to build, and it was built by a team that changed over the years. But finally they worked, and we built about 50 of them. And these things were machines that had 3 times the power of a VAX 11780. And for those of you who can remember that far back, academic departments used to run entirely on a single 780. We ran the software for a single user on a machine that was 3 times as fast. So we could really do good stuff. It was still 16 bits, but it had virtual memory, so you could pretend it was bigger. We also did things like overlays, for those of you who are old enough to remember what an overlay is. We tried to build a multiprocessor called the Dragon, but I had left by the time that program came to fruition and never really went very far. We built, as I said, a lot of gadgets of various kinds. So the software, well, there were 3 operating systems that were built. There was the original Alto OS, which was actually a copy of an operating system called, I can't remember what it's called, but it was by 2 guys in the UK called Stoy and Strachey. And they had built this nice single-user machine operating system, and we copied it. It was written in BCPL, yes. We never ran a significant amount of assembly code on any of the machines at PARC. We went to BCPL from day one. We had a BCPL for the Nova. We looked at using Algol, but it turns out that Data General Algol had the interesting problem that if you gave it 2 real numbers and the answer was between 128 and 256, it was wrong. That kind of problem nearly sunk Intel a few years later when they had a little problem in their floating point unit. But in any case, yes, that was BCPL. And I meant to ask a couple of slides ago, what's wrong with this picture? Can anyone tell me? It's very subtle. Pardon? I'm sorry? Oh, that's a typo. I'll tell you what the error is. The description of what an instruction does uses C syntax. At that time, there was no C. But I figured it would be, anybody who wanted to drill into this might prefer to have it made modern a bit. Okay, we wrote an operating system in the so-called System Development Division, which was one of the commercial attempts that Xerox made, called Pilot. And we built an operating system called Cedar, which is the primary operating system for the Dorado. That was written in Mesa, which was the language that we developed. Get to that in a second. Yes, there were two and a half commercial entities that were set up to capitalize on the Alto. One was the System Development Division, and another was an exploratory thing that was set up to try to sell the Alto as a word processing system. But of course, we were competing against the Star, which was quite a bit cheaper. And so that didn't work out well, except for one thing, which was that they produced a text editor called Bravo X, which every one of you uses the direct linear descendant of today. It's Microsoft Word. Charles Simoni, who was responsible for Microsoft Word, came from Xerox PARC, where he had originally built it. Yeah, here are the languages. BCPL, which was the forerunner of C, of course. Mesa, which was a Pascal descendant language. Cedar, which was a functional language, as I recall. And of course, several versions of Smalltalk, and one version of Lisp. Although Lisp was never very successful on the Alto, it was on the Dorado. On the Alto, there just wasn't enough memory for it. And Lisp is a kind of a memory hog. And so, although Peter Deutsch had written a special emulator for the Alto, that's another thing that we did. We tried out all of these machines by changing the microcode. So we could change instruction sets willy-nilly. In fact, you could do it dynamically. You could have a Smalltalk program, call a BCPL program, and then come back. We've only recently regained that capability in things like Visual Studio, the ability to have to do multilingual development. Okay. Alto was great for applications, and we tried out a lot of things. We built Bravo and Gypsy. Gypsy was a specialized version of Bravo that was used by a book publishing company that Xerox owned quite successfully, Ginn and Company. Some of the first Books to be typeset using laser printing were done on Gypsy. We built the Laurel mail system, which looked very much like today's mail systems. And of course, because we had a company-wide network based on Ethernet with high-speed links going between various Xerox facilities, we had email to 5,000 people by the end of the 70s. The ARPANET was just getting off the ground at that time. We had numerous drawing applications because, of course, people who were interested in drawing applications flocked to the Alto like bees to honey or to flowers because they could do such a wide variety of things with that bitmap screen. So I wrote a thing for drawing logic diagrams because I believe that the purpose of a computer system is to run the CAD tools to build the next generation. There was a language called markup for editing bitmaps. Today that's called Microsoft Paint. There was a program to draw spline curves. And you see that today in things like Visio. If you've used Visio, when you draw a freehand curve, what you're actually drawing is a spline. Except I actually believe that the way Draw constrained the splines was actually better than the way Visio does it today. Because Visio is trying to hide from you the fact that there's a mathematical operation down there that you can actually control, things like the first derivative of the curve as it goes through a point. We try to fake you out on that, and the result is sometimes humorous and sometimes infuriating. So we also had a thing, there were no fonts in those days, right? Fonts were all 5x7 bitmaps. And so if we wanted to print in a new font, we had to design it and build it. And one of the things that we discovered early on, and this was of course done by John Warnock and Chuck Geschke, was that splines were a really good way to describe a font. And of course that was the basis for TrueType, which went on to build Adobe. Although Adobe still doesn't seem to be able to get mice right. 2 minutes. Okay, there were a lot of servers built. And one of the things you have to understand is the Alto by itself was not interesting. It was the distributed system aspect of the Alto that was really the thing that was good, and that required servers and a network. Well, we had the network. We didn't quite understand initially how important servers were going to be, but they were, of course. And printing was the poster child for servers because the printers were just so expensive that you couldn't afford to give one to every person. You can today, in fact, but you couldn't at that time. And so we shared them, and the first one was ears. And then we had a language for page description called Press and then Interpress. And those were the forerunners of Adobe PostScript. And in fact, PostScript was developed by Warnock and Geschke before PARC. It was a language called JAM, John and Martin. But we had a lot of file servers because the Alto didn't have very big disks. And so when you have file servers, you no longer had to change those cartridges in and out. You could just swap to the server. There was the interim files. I don't remember the Woodstock file system. Yes, Woodstock file system was a bust. The interim file system was not interim. We used it for 7 years or something like that. Juniper was an object store before people called them that. I don't quite remember the details of Alpine. And then, of course, our mail system, which actually is very reminiscent of the mail systems today, was called Grapevine. It had most of the things that you see in internet mail today. Mail servers that do nothing but receive and deliver mail, and distributed replicated storage so that you never lose your messages. A lot of things aren't very much different today than they were then. Various communications stuff. PARC Universal Packet which of course was the PUP was the forerunner of the IP protocol that's used today. We went to all the meetings when IP was being developed, and we were told by, I didn't go, but the people who did were told by the Xerox lawyers, you're allowed to ask clarifying questions, but that's all. Don't say anything about what you've been doing. And so they went to these meetings, and somebody would say, oh, we ought to do it this way. They would say, well, will the following be a problem? And after a couple of hours, apparently one of the guys on what would have then been the IETF turned to the Xerox guy and said, you've done this before, haven't you? A lot of people think that the first worm was the Morris worm, but it wasn't. It was actually an earlier worm, and if you give shock, S-H-O-C-H, HUP, to a search engine, you might find it. They were trying to do the same thing that Robert Morris was doing, except he did a lot more damage. This worm just shut down every Alto and PARC to the point that we had to power them all down and clear out the virus from the disks and restart them one by one. It took a couple of days. We tried to do various things to make some money at this game, mostly failing. As I said, there was SDD, which did an office suite, the Palo operating system, and the Star computer. That's the computer that people generally talk about as being the forerunner of the Apple Visa. Maybe. But it was too expensive. The ASD did market probes, as I said. They foisted Bravo X on the world. We built some Lisp workstations out of the Dorado and Dolphin, and one of the other Xerox divisions tried to sell them, but that didn't go very well. So over its life, the population of the Alto was about 1,500 systems. Not a huge amount by the standards of today's PC business, but given that it was expensive as it was, it demonstrated to us that there was something there. Unfortunately, it didn't demonstrate that to Xerox management. And as a result, we all finally gave up in disgust and went off to a company that actually built computers, DEC. So the successors of the Alto, well, lots of extinct scientific workstations. Back in the 80s, we didn't have personal computers yet, really. They were just coming into existence. They were very wimpy. In fact, one of the first personal computers, the Apple I, used a 6502 microcontroller chip as its CPU. We actually used the 6502 as the keyboard controller in the Dorado. So we thought of these things as toys. But of course, a lot of people didn't, and so that's how we got where we are today. Sun Microsystems grew up out of the Alto. They wanted one. They wanted them, but we couldn't sell them. And so they did what we did with Macs. They built their own and built a very successful company out of that. And of course, the Apple story everybody knows. Adobe was formed by Warnock and Geschke out of PARC. And of course, PARC had both most of the features of Windows and Microsoft Word in 1973, which was 2 years before Microsoft actually existed. No, they were, we knew about Apollo, but they were a workstation company, right? Yeah, that's right. They were Sun competitors. Well, perks were actually funny because the perk was designed by a guy named Brian Rosen, and Brian worked for me when I was working at the System Development Division, and he decided that he liked the idea of building personal-like computers so much that he would go back and he founded a company called Three Rivers Computer, and built these machines. But what I'm told is that PERCs never worked. They had a lot of problems because there were a lot of shortcuts taken in order to make the price low. But yeah, I never ran across Brian ever again. And of course, here's the crew about the time CSL dissolved. And you can see me in the back row. The three people to the extreme right are Roy Levin, Andrew Birrell, who did the Grapevine mail system, and Mike Schroeder, who is the guy who invented protection rings when he was a graduate student at MIT. Those guys are now about 20 feet away from me down the hall. Bob Taylor is in the middle of the first row. Bob is clearly the best manager for research that the world has ever seen. We will never see his like again. So I thank you very much. I'll be happy to take any questions, and thank you again for the opportunity to join you.
If you'd like to ask Chuck questions, please push the button on the microphone in front of you, and that way the video will also pick you up.
No. I mean, where do you think all the interesting computers in the world go today?
Actually,
Uh-huh. It was quite pleasant. I haven't actually enjoyed programming. I won't program in C, for instance, because I make too many mistakes. I demand a type system. So Cedar had one, and when I left Xerox, I felt I had stepped into a time machine and gone back about 10 years. But it's gotten better, and now you can program in languages like C# and things work just fine. Program in Java too, although apparently that's getting to be a pretty risky business. Yeah.
I mean, most of the exciting stuff happened around the time when I was born. The question is this golden age of the computer time, can this be repeated? What's the real?
I don't think it ever ended, right? I mean, there's an exponential curve going here, and the thing about exponential curves is you look back and you look forward, and they look about the same. I think that you guys have the opportunity to do things that are just as exciting and, frankly, just as remunerative as the stuff that we did 40 years ago. And the reason is that applications for computers keep growing. The machines are not getting much faster, but there are a lot more of them, and so effectively they are. And think about the things that we never thought we would be able to do, like simultaneous translation from one language to another. We can now do that. We demoed last October a system based on deep neural nets that does simultaneous real-time translation from English to Mandarin. So, one of these days, I think when you pick up the phone to make a transcontinental or transoceanic phone call, ask you what language the recipient will be speaking. And of course, there are video games and the derivative technologies that people use GPUs for. I mean, think about things like the Kinect sensor. Now we have the opportunity for the computer to know what you are doing and know who you are and interpret commands in a new way. And we keep seeing more and more people building interesting applications for Connect since we made the software development kit available. And other people will do things like that. I mean, my own belief is that we've just touched the surface of tablet PCs. I mean, I worked 12 years ago. Microsoft actually introduced a tablet PC, but it never got traction because people weren't interested, because we were unable to push the software well enough. There weren't enough people inside Microsoft that were interested in the technology. It was basically Bill Gates, myself, and Butter Lamson. And that's just not enough when you've got an organization that size. So it languished for 10 years until Jobs picked it up. But I believe that he made a critical mistake by not adding the stylus. I mean, what he said is, if you need a stylus, you failed. And he was right in that you failed at being the optimal consumer consumption device. But there are a lot of people who want to enter stuff into the computer. And many want keyboards, but many would prefer to handwrite. And we know this to be a fact. In fact, one of the niche markets for tablets was university professors. Why? Very simple. They could write on their slides when they lectured. Okay. Anybody else?
So
Okay.
if no one else has a question, I do have one.
Okay.
And you touched on it. You touched on the fact that there was something really magic, that there will never be another Bob Taylor. And I've spent a fair amount of my life looking at research labs and trying to create environments that really inspire people. Can you say a few minutes, talk for a few minutes more to some of the people here who are going to be leading and creating technology development enterprises about what's the magic that happened at PARC that caused so many people to work so collaboratively and to benefit from each other's wisdom, the likes of which very few other organizations have been able to duplicate?
Well, it was very interesting, and many people have tried to write this down. What Bob believed in, you have to remember something. Bob was not a technologist. He was a psychologist. He didn't know how computers worked. He didn't know how to program. All he knew was how to pick people and how to build an environment that would allow those people to work together with no outside interference. And managers in the technology field tend to be either inward-looking or inward-focused or outward-focused. If they're inward-focused, they're interested in being conduits for direction from above that are disseminated to the troops. The other guys stand facing outward and deflect idiocy when it comes at you. And that's what Taylor did, and he was brilliant at it. The reason that he finally got mad and we all left was because he ran up against a manager that wasn't going to put up with that, and he wasn't going to turn around and manage inwardly. So that's part of it. Part of it was he had worked at ARPA as the director of the Information Processing Techniques Office, which had the property that it funded most of the graduate careers in computer science up to 1970. And so he knew everybody in the field. And he knew who were the good guys, who were the bad guys, who were the marginal guys. And when they chose him to start CSL, I don't think George Paik actually knew what he was getting into, because Taylor just went around and picked up all his old friends. And he didn't actually support my graduate education because I don't have a graduate degree, I'm afraid. But I snuck in on other people's coattails from BCC, which worked out pretty well. What did he try to do? One thing he did was he kept his laboratory flat. That is, there is no internal structure. There's no sub-level of management. And we do that at MSR Silicon Valley today. That works up to a size of about 80 to 100 people, and it does not work above that. You have to have structure. So it's a puzzle, because what happens when you get that big? Do you set up another laboratory? Do you use structure? I mean, Microsoft Redmond uses structure. There's about 4 levels of management. And the problem with doing that is that you get a situation where a group is individually big enough that they're at critical mass, which means that they only talk to their colleagues. They don't talk to other people. And so another thing Taylor insisted on was that there be only one coffee pot in the building, and it'd be in a centralized location. Because you went to get coffee, you would run into someone and you would say, "What have you been doing lately?" So there were a lot of the best projects, including some of the ones I described here today, were done by collaboration across the entire range of people, from computer science theorists to hardware people. Those were the ones that really paid off. Anything else? Stay small. Deflect the crap. Every hire should raise the average IQ. That's right. This has been written down by Roy Levin in a paper that is in a sort of a Festschrift for Roger Needham, but that was not widely published. Maybe it's on Roy's website. Okay, anybody else? Fine.
Okay, this has been a wonderful opportunity. Thank you very much.